So we are now starting the exercises 7.2. I will leave out the routine computational ones. That's why I am not starting with number 2. Instead we start with number 4, where we have to establish some assertions. There are a few of them. This is the first one, where we have to prove that if n is an odd integer, positive integer of course, then the phi value of 2n equals the phi value of n. The solution is pretty easy because n is odd, so the GCD of 2 and n will be equal to 1, and that is why since phi is multiplicative, phi of 2n will be equal to phi of 2 times phi of n. Now phi of 2 obviously is 1, so that's how you are getting phi of n. Next we have part B, where we have to prove that if n this time is even, n is an even positive integer, then phi of 2n equals 2 times phi of n. So in the solution, in the beginning itself, we make use of the fact that n is even. So n will generally have this form 2 to the power k times m, where the evenness of n makes k positive. K won't be 0. It may be 1 or something larger, but it will not be 0. And this other part m is odd, it's not divisible by 2. So then we consider the left hand side of the desired equality, phi of 2n. So this is phi of 2 to the power k plus 1 times m. I mean you use this thing here. And then because m is odd, so 2 to the power k plus 1 and m are relatively prime. There is no common prime factor. So that's why the multiplicative nature of phi allows you to write it like this product. Now you know how to calculate this number times 1 minus 1 divided by 2. So which just is 1 divided by 2. So you have to divide this by 2, obtaining this. And along with that phi of m remains. And then you can split this further like this, 2 times 2 to the power k minus 1 times phi of m. Just like phi of 2 to the power k plus 1 is 1 half of it, this is also 1 half of 2 to the power k, which is just its phi value. And then because this 2 to the power k and m again are relatively prime, so you can merge them like this, again using the fact that phi is multiplicative, which however is phi of n. So that's how you get the equality. In part C, we have to prove that phi of 3n is 3 times phi of n if and only if 3 divides n, and where n of course is a positive integer. Because this is an if and only if statement, so there are two halves. This half is almost like what you saw just now in part B. So where we assume that 3 divides n, then n will be of this form. In part B you had the beginning that n is divisible by 2. That means n is even. Here n is divisible by 3. The rest is almost the same. So n has this part 3 to the power k times m, where k is positive and m is not divisible by 3. So then we consider phi of 3n. 3n becomes this and this are relatively prime because 3 does not divide n. So you split them like this, and then you calculate this part just like how you calculated that one, and the calculation gives you this. And here then again you can split this 3 to the power k like this, and you keep the 3 to the power k minus 1 with 2, because if you calculate phi of 3 to the power k, that just becomes this. It's a simple thing, right? And then you can understand what the next step would be, because this 3 to the power k and m are relatively prime. By the multiplicative nature of phi, you can merge them together and have this, which then becomes phi of n. So that's how you are getting phi of 3n is equal to 3 times phi of n if n is divisible by 3. And now we will go for the converse. The proof of the converse is actually shorter. Conversely, let phi of 3n be equal to 3 times phi of n. Now what is it that we want to prove? We want to prove that then n is divisible by 3. Suppose that's not the case. Suppose 3 does not divide n. Then phi of 3n would be equal to phi of 3 times phi of n, because n and 3 will now be relatively prime. Note carefully that this non-divisibility immediately implies that the GCD of 3 and n is 1 because 3 is prime. That's why. But anyway, now we have this, and phi of 3 you already know is 2. So from your hypothesis, this is equal to 3 times phi of n, but because of your supposition, that is also equal to 2 times phi of n. So subtracting 2 phi of n from both sides, you get phi of n equal to 0, which of course is not possible because no phi value is 0. And that's why our supposition is wrong. That means we must have n divisible by 3. So that's the proof. Next we have part D. In part D, we have to prove that for any positive integer n, phi of 3n equals this time 2 times phi of n if and only if 3 does not divide n. One half of the solution is already ready for us. We don't have to do anything, because if 3 does not divide n, see, we have already shown that phi of 3n is equal to 2 times phi of n. So now we just have to prove the converse. Conversely, let phi of 3n be equal to 2 times phi of n. And we want to now show that 3 does not divide n, but suppose it does. Suppose 3 divides n. Then by part C, phi of 3n is equal to 3 times phi of n, because that's what part C says. So this becomes equal to this. And then you again get the impossibility that phi of n is equal to 0, which I just simply wrote like this, so we get a contradiction. You know what to write here. That's same thing. So that's why this cannot happen. That means its negation should happen. That is, 3 should not divide n. So that's the proof. And finally we have part E, where we have to prove that phi of n is 1/2 of n divided by 2, if and only if n is a power of 2, where the exponent is a positive integer. This is 1/2 of the solution, which is pretty easy. If n is equal to 2 to the power k, where k is positive, then phi of n is 2 to the power k minus 1, which really just is n divided by 2. I have not shown this calculation in more detail because by now you know how to calculate these things. So you supply the missing steps here. Conversely, let phi of n be equal to n divided by 2. Now because phi of n by definition is the number of integers satisfying so and so conditions. So this is an integer, so the right hand side must also be an integer. So that's why in particular this means that n is even, n is an even number. Otherwise this side will be a fraction. So because n is even, n will in general have this structure, 2 to the power k times m, where k is positive. Had n been odd, k would have been 0. Because n is even, so k is positive and the other part is not divisible by 2. That means that is not even. So now we consider 2 to the power k minus 1, which is 1/2 of n, n divided by 2. And by our hypothesis, that is equal to phi of n. But n is 2 to the power k times m, and 2 to the power k and m are relatively prime. So you split it like this, and this will be equal to 2 to the power k minus 1. You know how. And this one is phi of m. So we can cancel 2 to the power k minus 1 from both sides, obtaining phi of m equal to 1. Now immediately this does not tell you what exactly m is. Phi of 2 is also 1, phi of 1 is also 1. But m is odd. So m can only be 1, it cannot be 2. And that's why if you then go back to this equation and put m equal to 1, you get n equal to 2 to the power k. This is what we wanted to prove, and here k is also positive. So that's where the entire solution ends.